All right, so today I'm just going to go over some things that a lot of people have been asking, a lot of email questions I've been getting, and just a lot of things that people seem to still have a little bit of trouble with. So I'm going to hopefully try to clear some of that up. The first thing I want to go over is Lorentz Force Law and the right-hand rule with the Lorentz Force Law a little bit more carefully. So the first thing to remember is that the cross product is not commutative. So that means that A cross B is not the same as B cross A. So you have to be very careful when you're doing the order of your cross product, and when you have a equation with a cross product in it, you have to be very conscious of what order the vectors appear in. So for example, when we do the Lorentz Force Law, we have QV cross B. That means that when you're doing the right-hand rule, you have to put your palm in the direction of V like this, and then curl your fingers in the direction of B, and it has to be in that order. If you do it in the wrong order, you're going to get the wrong direction as your answer. So always your hand goes in the direction of V, you curl your fingers in the direction of B, and then your thumb will point in the direction of that final vector, F. Okay, so that's the first thing to be very careful of. The other thing is that if you're doing working with negative particles, so if we're doing something with electrons, remember if this is negative here, that will flip the sign of your vector. So for example, again, remember our trusty little cross product circle here. So let's say, for example, that we're doing a problem and V is in the x hat direction and B is in the y hat direction, okay? And we want to take the cross product of that. So we want to do Vx cross B y hat. Now we can see here that x hat cross y hat will give us z hat. So we're going to have QVB in the z hat direction. But this is if Q is positive, right? If Q has a positive sign, then it's just going to be QVB in the positive z hat direction. But if Q has a negative sign, then it's going to negate the whole this whole side of the equation, right? So then, if we have a negative particle, then our force will be in the opposite direction. Now, the way that I handle that with the right-hand rule personally, which I think is easiest, is just do your right-hand rule like normal. So if we're doing, let's say the x hat is in this direction, the y hat is in this direction, so just put your palm in the x direction, curl your fingers in the y direction, and your thumb will point in the z direction. So say, okay, that's my right-hand rule. Now, if I'm doing this for a negative particle, all I have to do is then say, okay, well, if it's negative, then it will be opposite. And that's all you have to do. So just do the right-hand rule like normal, and then at the end, just add in that negative sign and flip the direction. So that's personally what I think is the easiest way. That way, it's very easy to lose negative signs and stuff. So just do your right-hand rule like normal for a negative particle, but then at the end, just add in that negative sign and flip the direction. Okay, and then if we were, let's say we had a positive particle, but we were just trying to do, let's say, negative x hat cross y hat. What does that equal? So again, what I would do is just ignore that negative sign for a second. So just ignore this. Say, okay, what is x hat cross y hat? Well, x hat cross y hat we know is z hat. And then just add in the negative sign at the end. So you can kind of just ignore that for a second, figure out what x hat cross y hat is, and then add it in at the end. And then the same thing if you had, let's say we were doing negative x hat cross negative y hat. Ignore the negative signs, say, okay, I have x hat cross y hat, that will give me positive z hat, and then two negatives, just like with multiplication, two negatives will give me a positive, so I still get positive z hat. So that's the way I handle negatives with the cross product, is kind of just ignore them at first, do the cross product with all positives, and then add your negative signs in at the end. That to me is like the least likely way to make a mistake. Alright, so another thing to keep in mind with the cross product is, this was one of the homework problems, I think 27.15. So this was from 27.15. We had a proton that was entering, there was some magnetic field in here. We didn't know what direction it was or what magnitude it was. And we were trying to find the magnetic field, both the magnitude and direction. Okay, so we're going to use the Lorentz Force Law here. So we know that F is equal to QV cross B. Now, in order to find B, so we know what direction V is in, and we know what direction F is in, right? So V is in this positive direction here. We can call that the positive y-axis. So we'll just say that our axes are y going like this and x going like that. So V is in the positive y direction. We see that as it enters this magnetic field, so right here when it enters the magnetic field, the centripetal force is directed inward, right? The centripetal force is directed that way, because when it goes in a circle, remember for uniform circular motion, the force is directed inwards towards the center of the circle. So right when it enters the magnetic field, the force is directed inward. And then we have to figure out, well, what direction is B then? So what I noticed was that a lot of people were doing V cross F to get B. And that's not correct, because remember, the cross product, you can't just flip things like that. So if you do V cross F to get B, you're going to end up with an extra negative sign that's wrong. So what you have to do is say, okay, well, V cross what will give me F? Okay, so what I would do for this is say, okay, I'm going to point my hand in the direction of the velocity, so I'm going to point it straight up in the y direction. I know that my thumb ends up pointing to the right. So what direction do I have to curl my hand in order for my thumb to be in the direction of the force? Because we know the force is pointing towards point B. So how do I have to curl my hand in order for my thumb to be pointing in the correct direction? Well, if I point my hand again in the direction of V, if I curl my hand this way, my thumb is pointing to the left, so that's not right. If I turn my hand this way and then curl my hand out, then my thumb is pointing in the right direction. So B has to be out of the page here. So B is coming this way. That's because when I put my hand in the velocity of my hand in the direction of the velocity, the only direction I can curl my fingers in so that my thumb is pointing in the right direction is out of the page. So B has to be out of the page. So that's something to keep in mind when you're doing these problems. Again, be very careful of the order that you're putting your vectors in when you do the right-hand rule, because that does matter. Okay, another thing I want to go over is cyclotron motion again, and why I'm only using certain components of the velocity when I do cyclotron problems. So this problem is from lecture 13. It's page 20. And it's the example where we have a proton with a velocity given by this, so the velocity is in the x and z hat direction. It enters a region with a magnetic field of 0.5 Tesla directed along the x-axis. So the magnetic field is directed along the x-axis only. We want to find the force on the proton and its acceleration as it enters the magnetic field, and the radius of its path and its angular speed. Now I'm realizing I had a bunch of errors here. Anyway, so we want to find its force and its acceleration. So since the velocity cross the magnetic field is a cross product, part of what a cross product is it means that those two vectors that you're taking the cross product of, they only interact in their perpendicular components. So only the components, if we have V and B, that are perpendicular to each other interact. If they have a parallel component, those parallel components don't feel each other, because the cross product takes two perpendicular vectors and returns a third perpendicular vector. So only the perpendicular components interact in a cross product. And you can see that here, when I calculated the cross product, I put in V, so V has the x and the z hat, and then I put in B. And you can see that the x component of the force ended up being 0. And that's because the parallel component of V and B just cancels out. The cross product does not pick up parallel components. So the parallel component of V with B just ended up being 0 in the resultant vector, and only the perpendicular component was non-zero, right? So the z direction was 0, and then only the y hat direction was left, because that's the only direction here that's perpendicular to both vectors. So when I found the acceleration in the second part, I only used vz here because that's the only component of the velocity that the force feels, right? So look back here, the force only had vz in it. It didn't have vx, it didn't have the x component of velocity. It only had the z component. That's because the magnetic force only feels the component of velocity that's perpendicular to the magnetic field. So that's why in cyclotron motion, you want to just pick out that perpendicular component of velocity, and that's the one we use when finding the radius, the cyclotron radius, or the force, because the magnetic field doesn't even really know that the parallel component of velocity is there. So again, since the force, the magnetic force, is a cross product, only perpendicular components contribute to that force. So that's why I only used Vz here, is basically because of that cross product. Okay, and then let's go over the right-hand rule. So I did the right-hand rule with the Lorentz force already. And there's also like a right-hand rule for cylindrical coordinates, essentially. So when we're doing problems where we have a magnetic dipole, a wire, a solenoid, a toroid, I think that's everything, a wire loop, and we want to find the magnetic field or vice versa of any of these, we use a cylindrical right-hand rule. So the cylindrical right-hand rule is a little bit easier because there's really only two directions you have to worry about. You really only have to worry about like the phi hat and the z hat direction. So I'll say here like this is the z hat, and then this is like the phi hat direction, essentially. So our fingers are like the phi hat direction, they curl around something, right? And then our thumb is like the z hat direction, it just points straight in one direction or the other. So since there's only really two directions, there's not really a lot to worry about, like with the right-hand rule with Cartesian coordinates, where you have three vectors to worry about. So, you know, for example, when you're given a wire loop, like a dipole or just a loop of wire, you just put your hand in the direction of the current and your thumb is in the magnetic field, and that's all you have to worry about. There's only two directions. The same thing with a solenoid. Just put your hand in the direction of the current, your thumb's in the direction of the magnetic field. If it's the opposite case, where let's say the current is actually straight, then you just put your thumb is the only straight thing here, your hand's not straight, so you just put your thumb in the direction of the current, and then your hand curls in the direction of the magnetic field. So basically, whichever one is curling, your hand goes around that way. Whichever one is straight, your thumb goes that way. And that's really all you have to worry about. There's only two of them, so you don't have to worry about the order or anything like that. Okay, so let's just see this a little bit more carefully again. Let's just go over Ampere's law quickly. So Ampere's law you absolutely need to know how to do for the final. If you don't know anything else besides like Ampere's law and the Lorentz Force Law, like know those two things. So let's just go over Ampere's law quickly. And again, just like Gauss's law, there's only a couple of scenarios where you can use Ampere's law easily. So the only times you really need to use Ampere's law are for a current wire or a cylinder, a solenoid, or a toroid. So just like with Gauss's law, where we just had the spherical, cylindrical, or plane symmetry, with Ampere's law, we kind of have the same thing, where we just have the current wire or a cylinder, a solenoid, and a toroid. So make sure you know how to use Ampere's law for those three scenarios to find the magnetic field. So just quickly, for a current wire, so if we just have a current wire, let's say with current going this way, and I want to use Ampere's law to find the magnetic field, I'm just going to do B dot dl is equal to mu naught I enclosed. B and dl is just a loop around the current that way. So it just loops around the current. And the circumference of that loop is 2 pi r. And then my enclosed current is just I. So the magnetic field of a wire is just mu naught I over 2 pi r. So this is definitely something you need to know. it's helpful to just memorize this final answer. So if something on the final uses the magnetic field of a current carrying wire, you can just immediately write this down, and you don't have to do Ampere's law to solve for it and maybe introduce some errors into your exam. So I would just memorize what the magnetic field of an infinite current carrying wire is, but then also make sure that you know how to use Ampere's law to derive it. Okay, and then we can use the right-hand rule to figure out what direction the magnetic field is going in. So I point my thumb in the direction of the current because the current is just straight down. So I just point my thumb in the direction of the current, and then my hand curls in the direction of the magnetic field. So my hand is like coming out of the page at the top and then going back in at the bottom. So it's kind of, it's coming out up here and then going back in down there. Okay, so that's a current carrying wire. Let's do quickly a solenoid. So remember, an infinite solenoid, or one that we can approximate as infinite, it has some current going around on these wires, let's say that way, and it has n turns per unit length, and they each carry current I. So in order to find the magnetic field, I'm going to use Ampere's law. So I'm going to draw my Amperian loop in here. And then, again, I'm not going to go through the details. This is in our Ampere's law lectures where I go through the actual integral. So this comes out to B times L is equal to mu naught times the number of turns per unit length times L times I. So my magnetic field ends up being mu naught N times I. So again, the details of this and how I actually, count each contribution and why I choose here is in chapter 28 lecture. So I just want to show you here like the final answer. So make sure that you remember, just memorize the magnetic field of a solenoid. Now again, for the right-hand rule, since now my current is curling, so I curl my hand in the direction of the current now, and then my thumb points in the direction of the magnetic field. So in the case I drew here, my magnetic field is going upward because my hand curls this way and then the magnetic field is up. So the magnetic field goes like that. Okay, and then let's do a toroid. So that's the last main case. So a toroid, remember, is kind of like this solenoid that's sort of like looped back in on itself to make a donut shape. So a toroid is kind of shaped like that. Okay, so a toroid is kind of like a solenoid. If you like take two ends of a solenoid and wrap them around into a donut shape, that's a toroid. So a toroid, we can use Ampere's law, and we're going to have B dot dl is equal to mu naught I enclosed. So here our Amperian loop is going to be inside like the donut of the toroid. So our Amperian loop will be inside here, because we know outside a solenoid the magnetic field is 0. So out here the magnetic field is 0, and then right in the center here the magnetic field is 0. So we have B, this is just a circle, our path, so it's just 2 pi r. And then we have mu naught times I enclosed. So what is I enclosed? Well, it's how much current is enclosed in this entire loop. So again, typically for a toroid, you're given n, which are the total number of turns, and they each carry current I. So the total enclosed current in this loop is the number of turns times I, right? So you have like 50 turns, and they each have current I. 50 times I is the total enclosed current. And then just divide by 2 pi r. So you get B is equal to mu naught capital N I over 2 pi r. So again, just memorize this result so that you can immediately just write down the magnetic field if you're working with a toroid, and make sure that you're comfortable getting from here to here. Okay, so these are the 3 main cases of Ampere's law. And then again, for the right-hand rule for a toroid, just pick somewhere on the toroid. So like, let's just say, okay, right here. So right in this little spot here, the current is coming out, so it's coming like up and over. So I just put my hand in the direction of the current like this, because it's coming out from the bottom and then over the top of the donut. So then my thumb will point in the direction of the magnetic field. So my thumb is pointing to the left in that case, and that's going to be the case for anywhere around the magnetic field. So that means the magnetic field is going in this direction around the toroid. So it's going clockwise in this case. So that's how you use the right-hand rule for a toroid. Okay, and so these are the three main cases for Ampere's law. So make sure that you know how to do all three of these. Okay, and then the last thing is just Faraday's law. So this is another one. Make sure that you remember this equation, and then the flux is B dot A. So make sure that you know how to calculate the flux. It's just the magnetic field dotted into the area of whatever we're looking at. And then the EMF induced in some area, some wire, will just be equal to the time rate of change of that flux. And then you can determine the direction. So the direction is like this negative sign here. You can determine the direction with your right-hand rule. So then for Faraday's law, make sure that you go over the problems for Faraday's law that we did in lecture, that you did in discussion today, that we did for homework, because all of these things will definitely pop up on the final. Faraday's law, Lorentz law, Ampere's law, they will definitely be on the final. So make sure you know how to use them. Make sure you know how to calculate the flux in an area. Make sure you know how to use the right-hand rule to figure out what direction the current will be in from Faraday's law, which again, you can just use the right-hand rule for that. And then again, I know since I said there's going to be no currents, I don't want anyone to be worried about like currents popping up with Faraday's law, because sometimes they'll say like, oh, there's a resistance in this circuit, find the current. I'm not going to put anything complicated with circuits at all. The most that you'll have to do with circuits is that you'll just have an EMF. I'll say this is the resistance, find the current, and then all you have to do is just use this equation, which is on your formula sheet. So that's the most that you'd have to do with anything circuit related. So don't worry about that. Okay, so those are the main things that I've been getting a lot of questions about. So just remember that to do a lot of these problems, as you've been seeing from the homework, you do need to remember some basics from chapters 21, 22, 23. So you still need to remember electric field, electric force, potential energy. Those are the kind of things you need to remember from those chapters. But again, the homework and the problems that we've done in lecture are very good representations of what you need to know. So I would just focus on those problems, the lecture problems, discussion problems, and if you can do those, if you can do the homework problems, then you should be fine, and you really, you shouldn't have anything to worry about. Okay, so yeah, I think that's really it for the review today. Those are the main things I've been getting asked about.